In a Greenland ice core drilled in the early 1990s, there is a thin layer dated to the year 536 AD where sulfate concentrations spike to levels not seen in over 1,000 years. It is a quiet line in the chemistry, just a few millimeters of frozen atmosphere, but it marks the moment when something filled the sky above the entire planet. The sun dimmed. Summer temperatures dropped so far that frost formed in July across China and Ireland alike. And for reasons no one alive at the time could name, civilizations that had stood for centuries began falling into silence. What left that mark in the ice? That question haunted researchers for decades. The written records were there, Byzantine historians, Chinese imperial astronomers, Irish monks, all describing the same phenomenon from opposite ends of the world. A sun that rose but gave no warmth, a sky that never fully cleared, harvest that never came, but the cause remained hidden, buried in ice sheets and tree rings and volcanic glass too small to see without a microscope. Tonight we follow three traces left behind by that event. Chemical signatures locked in ancient ice growth rings, frozen mid-season in 1,000-year-old trees, and the silent archaeology of cities abandoned so quickly that gold was left in the ground. We are not here to prove what happened. We are here to listen to what the evidence whispers. The year 536 AD has been called the worst year to be alive in human history. The phrase belongs to medieval historian Michael McCormick of Harvard, and it carries weight, not because it is dramatic, but because the evidence behind it is so quietly overwhelming. Not the Black Death, not any single war. A year when the sun itself seemed to fail, and the consequences unfolded across continents, like a slow exhale that never ended. To understand what the ice cores recorded, you have to understand how they work. Every winter, snow falls on the Greenland ice sheet. Every summer, that snow is buried beneath more snow. Over centuries, the layers compress into ice, trapping tiny bubbles of ancient atmosphere and whatever particles were drifting through the sky when that layer formed. Drill down far enough and you hold a cross-section of the air your ancestors breathed. Pollen from vanished fields, dust from forgotten droughts, and when a volcano erupts with enough force to punch material into the stratosphere, sulfur compounds that settle across the planet and are captured year by year in falling snow. The 536 layer is unmistakable. Sulfate levels rival those from the 1815 eruption of Mount Tambora, the event that erased summer from the northern hemisphere and killed tens of thousands. But the ice tells a stranger story than a single eruption. There are additional spikes in 540 and again around 547. Not one catastrophe, but a cluster. A decade of volcanic bombardment that kept reloading the atmosphere with sulfur before it could clear. Some researchers point to Ilopango, a massive volcanic complex in present-day El Salvador, as the source of the initial 536 eruption. The geochemical fingerprint isotope ratios trace elements volcanic glass shards. Extracted from the ice shows a compelling match, though the identification remains debated. What is less debated is the scale. Estimates suggest between 50 and 100 million tons of sulfur dioxide may have been injected into the stratosphere. At that concentration, perhaps 5 to 10% of incoming sunlight would have been reflected back into space before it ever reached the ground. The arithmetic is plain: a sustained drop of just 2 or 3 degrees Celsius across multiple growing seasons is enough to collapse agriculture across an entire hemisphere. And here is where the numbers become human. The dendrochronologists, scientists who read climate history and the width of tree rings, found that trees across Europe, Siberia, California, and New Zealand all recorded their narrowest growth rings in over 1,500 years, beginning abruptly in 536. Bristlecone pines that had weathered countless droughts showed rings barely visible under magnification. The trees were not dying. They were holding still, waiting for warmth that would not come back for more than a decade. The written sources say the same thing, each in their own language of dread. In Constantinople, the historian Procopius, a lawyer by training careful with facts, not given to superstition, wrote that the sun gave forth its light without brightness, like the moon for an entire year. In China, imperial astronomers recorded yellow dust raining like snow and frost in provinces where July should have been sweltering. In Ireland, monks noted simply a failure of bread. Different continents, different scribes, no contact between them. and yet the testimony converges on the same quiet catastrophe. What followed the dimming was not a single disaster, but a cascade. Crop failures led to famine. Famine weakened populations. Weakened populations became vulnerable to disease, and in 541 AD, 5 years after the sky first darkened, the bacterium Yersinia pestis, the same pathogen that would later cause the Black Death, emerged in the port city of Pelusium in Egypt and spread across the Mediterranean world on grain ships carrying infected rats. The Justinianic plague, as it came to be known, may have killed between 25 and 50 million people over the following 2 centuries, striking in recurring waves every 15 to 20 years, never quite allowing full recovery. Empires that had seemed permanent buckled under the weight. The Eastern Roman Empire, at the height of its ambition under Justinian, abandoned its dream of restoring Rome. The Sassanid Persian Empire weakened by failed irrigation, and collapsing Silk Road trade developed fractures that would prove fatal a century later. In Mesoamerica, the great city of Teotihuacan, home to over 100,000 people, was burned, not by invaders but by its own inhabitants, then left empty. In Scandinavia, wealthy estate halls were abandoned so suddenly that gold hoards remained buried in the earth, never retrieved. The owners simply vanished, but not everyone disappeared. Some societies bent without breaking. Some adapted to the cold, reorganized around new realities, preserved knowledge that might otherwise have been lost. The question of why some civilizations collapsed while others endured is perhaps the most haunting thread in this story, and it has no single answer. Geography, governance, flexibility, luck, all seem to have played their part. Tonight we will not settle that question. We will only walk alongside the evidence. We will look at what the ice remembers, what the trees recorded in their rings, what the archaeologists found in abandoned cities and undisturbed graves. We will listen to the voices of chroniclers who watched the sky darken and tried to make sense of a world that had stopped making sense. And we will sit with the silence that followed the decades of diminished light, failed harvests and recurring plague that reshaped the course of human civilization in ways we're still tracing today. So let your breathing settle. Let the room grow quiet around you. We begin where the evidence begins, not with empires or armies, but with a thin layer of sulfate sealed in ancient ice, and then the faint chemical memory of a sky that once refused to clear. The record in the ice. In 1992, on the high plateau of central Greenland, a drill bit descended through 2 miles of compressed snow and ice. The project was called GIS-P2, the Greenland Ice Sheet Project, and its purpose was to extract a continuous cylinder of frozen atmosphere reaching back more than 100,000 years. Each metre of core represented roughly a century of snowfall compressed under the weight of everything that came after. The team worked in temperatures well below freezing handling sections of ice that had not been exposed to open air since before the Roman Empire existed. And somewhere in that long column of translucent white and grey sealed in a layer dated to the mid-6th century, there was a chemical anomaly that would take years to fully understand. The anomaly was sulfate, not the faint traces that appear in any given year from ordinary atmospheric processes, but a concentration so elevated it resembled the signature of the largest volcanic eruptions in the historical record. The sulfate spike in the 536 layer was comparable in magnitude to the one left by the 1815 eruption of Mount Tambora, an event that killed more than 70,000 people and erased an entire summer from the Northern Hemisphere. Yet for decades after the GIS-P2 core was analysed, no one could say with certainty which volcano had produced the 536 signal. The chemistry was there preserved with crystalline precision in ancient ice. The source was not, and that gap between what the ice remembered and what it refused to name would drive researchers across 3 continents for the next 20 years. To understand why a thin layer of frozen sulfate matters so profoundly, it helps to understand what ice cores actually preserve. The process is deceptively simple. Snow falls on the ice sheet each winter. In summer, a thin layer of slightly different density forms as the surface warms and refreezes. Over time, the weight of successive years compresses the snow into ice, and within each annual layer, tiny bubbles of trapped air and microscopic particles remain sealed. A chemical diary of what was floating in the atmosphere at the moment that snow crystallized. pollen from vanished meadows, dust from ancient droughts, sea salt carried inland by long-forgotten storms, and crucially volcanic aerosols, the fine sulfuric acid droplets that form when sulfur dioxide reaches the stratosphere, reacts with water vapour, and spreads across the planet in a thin light scattering veil that can persist for years before it slowly descends and is captured in falling snow. The 536 layer in the Greenland cores was striking enough on its own, but what made it extraordinary was the confirmation that arrived from the opposite end of the Earth. When researchers examined ice cores drilled from Antarctic glaciers and dated the same time period, they found a corresponding sulfate signal smaller but unmistakable. A spike in Greenland alone might indicate a northern hemisphere eruption, perhaps from Iceland or Kamchatka. But a simultaneous signal in both polar ice sheets pointed to something else entirely. A tropical eruption, one powerful enough to inject sulfur into the stratospheric circulation that flows outward from the equator and distributes aerosols into both hemispheres. Whatever had happened in 536, it had not been a regional event. It had touched the entire planet, and the pattern did not end with a single spike. As glaciologists refined their analysis, through the late 1990s and 2000s, the ice revealed a second major sulfate peak around 540 AD and a third near 547. 3 massive injections of volcanic sulfur in just over a decade, each one arriving before the atmosphere had recovered from the last. This changed the scientific understanding of the event entirely. A single large eruption, even one on the scale of Tambora, typically affects global climate for 2 to 3 years before the aerosols settle and temperatures recover. But when multiple eruptions occur in rapid succession, their effects compound. The stratospheric veil never fully clears, temperatures never bounce back. Instead of a brief sharp crisis, you get a decade-long suppression, a sustained dimming that agriculture and ecosystems cannot adapt to quickly enough. The quantitative picture that emerged from the ice was sobering. The 1991 eruption of Mount Pinatubo in the Philippines, the largest eruption of the 20th century, released approximately 17 million tons of sulfur dioxide and reduced incoming solar radiation by 2 to 3% for about 2 years. Global temperatures dropped by roughly half a degree Celsius, enough to cause measurable disruptions in agriculture and weather patterns worldwide. The 536 event, based on the sulfate concentrations preserved in the ice, may have blocked 5 to 10% of incoming sunlight over a much longer period. Some estimates place the sulfur dioxide output of the initial eruption alone at 50 to 100 million tons. The resulting temperature drop, perhaps 1.5 to 3 degrees Celsius sustained across multiple growing seasons, would have been unlike anything the planet had experienced in the previous 1500 years of human civilization. The difference between Pinatubo and the 536 cluster is not merely one of scale. It is the difference between a blow you recover from and one that keeps falling before you can stand. But the ice, for all its precision, could not say everything. It could confirm when the eruptions occurred. It could suggest their approximate power. It could indicate from the distribution of sulfate between hemispheres whether the source was likely tropical or polar. What it could not do was name the volcano. The sulfate particles carried a chemical fingerprint ratios of certain isotopes. Trace element compositions, the shape and chemistry of microscopic glass shards, but matching that fingerprint to a specific volcanic system required a different kind of detective work, one that would unfold over another 2 decades and involve mass spectrometers, electron microscopes, and painstaking comparison with ash deposits from candidate volcanoes around the world. That story belongs to a later chapter. What the ice could say with quiet authority was this: something extraordinary happened to the Earth's atmosphere beginning in 536 AD, something that loaded the stratosphere with sulfur on a scale rarely seen in the geological record. Something that did not happen once and fade but struck again and again across a single human generation. The frozen chemistry was precise, datable and legible, a planetary memory preserved in layers of ancient snow, waiting centuries for someone to learn how to read it. The question now was whether anything else remembered, whether the event sealed in Greenland ice had also been witnessed by human eyes, recorded in languages and scripts scattered across the ancient world by people who had no name for what was happening above their heads, but could not look away from a sun that had stopped giving light. Voices from the dimmed world. The Byzantine historian Procopius was not the sort of man to exaggerate. He had spent most of his career as a legal advisor to Belisarius Justinian's most celebrated general, accompanying military campaigns across North Africa and Italy, with the steady eye of someone trained to weigh evidence and separate fact from rhetoric. His major work, The Wars of Justinian, is a detailed account of imperial military strategy, methodical, measured, skeptical of supernatural explanations. He was in the modern sense a rationalist working in a deeply superstitious age, which is what makes the passage he wrote about the year 536 so unsettling. During this year, Procopius recorded, a most dread portent took place, for the sun gave forth its light without brightness, like the moon during this whole year, and it seemed exceedingly like the sun in eclipse, for the beams it shed were not clear. He was careful to distinguish this from an eclipse, a phenomenon he understood and could identify. This was something else, a dimming that lasted not hours but months, a sun that rose each morning and offered only a pale, weakened version of itself, as though the light were being filtered through something no one could see or name. Procopius was writing in Constantinople, the largest and most cosmopolitan city in the 6th century world, home to perhaps 500,000 people, and the administrative heart of the Eastern Roman Empire. His account would be remarkable enough on its own, but what transforms it from a single curious observation into something far more significant is the fact that he was not alone. Thousands of miles to the east, in a civilization that had no contact with Byzantine literary culture, Chinese imperial astronomers were recording the same phenomenon in entirely different terms. The Chinese kept meticulous celestial records. It was part of how they legitimized imperial authority, demonstrating that the emperor maintained the mandate of heaven by correctly tracking and explaining events in the sky. Their chronicles from 536 describe what they called yellow dust raining like snow, a haze so persistent that it dimmed the sun to a pale ghost barely visible through the murk. They noted frost in summer months in provinces where July temperatures should have been sweltering. They recorded crop failures so widespread that local officials eventually stopped keeping accurate mortality counts, not because the deaths were unimportant, but because there were simply too many to record. The convergence of these independent accounts is what gives the 536 event its particular weight as historical evidence. When a single source describes something extraordinary, scholars rightly approach it with caution. Exaggeration, misremembering political motivation, and simple error are all common in ancient texts. But when multiple sources from different civilizations writing in different languages with no knowledge of one another's testimony all describe the same phenomenon in the same time frame, the calculus shifts. In Ireland, monks working in separate monasteries recorded matching observations. The Annals of Ulster noted simply a failure of bread for the year 536, a phrase so spare it almost conceals the catastrophe it describes. In an agricultural society where most people lived season to season, where grain reserves were minimal and there was no global food trade to fall back on, a failure of bread meant famine. It meant watching stored grain dwindle with no prospect of replenishment. It meant communities beginning to fracture under the pressure of hunger that had no visible cause and no predictable end. Other Irish chronicles add a detail that deepens the picture considerably. They record that the summer of 536 was so cold the ground could not be tilled, not merely that crops failed, but that the earth itself refused to cooperate, frozen, too hard for planting, in months when farmers should have been tending growing fields. This distinction matters because it separates the 536 event from an ordinary bad harvest. A drought or a flood might destroy one season's crops while leaving the soil ready for the next planting. But frozen ground in summer meant the agricultural cycle itself had broken. There would be no planting, no germination, no harvest, and critically no seed grain saved for the following year. The failure was not a single season's misfortune. It was the beginning of a cascade. Around the Mediterranean sources describe a phenomenon they called the dry fog, a haze that hung in the air, constantly reducing visibility, making the sun appear weak and distant, but that lacked the moisture of normal fog. It did not feel damp, It did not dissipate with heat or wind. It simply persisted week after week, month after month, as though the atmosphere itself had changed composition. John of Ephesus, another contemporary historian writing from the Eastern Mediterranean, described how the darkness lasted for 18 months with the sun shining for only about 4 hours each day, and even that light being only a feeble shadow. Zechariah of Mytilene writing independently converged on the same figures: 18 months, 4 hours of dim light. Michael the Syrian, composing his chronicle several centuries later, but drawing on earlier sources, added that everyone declared the sun would never recover its full light. The consistency across these accounts, the duration, the quality of the dimming, the sense of a world suspended in permanent twilight, is precisely the kind of convergence that moves historians from curiosity to conviction. Perhaps the most psychologically revealing accounts come not from what people observed, but from how they interpreted it. A Syrian chronicle describes communities believing the world was literally ending, not metaphorically, but in the immediate theological sense. The sun failing was a sign of the end times in multiple religious traditions. Christians, Jews, Zoroastrians, and various pagan systems all carried prophecies about the sun darkening as a harbinger of final judgment. When it actually happened, when the dimming persisted month after month without explanation, people responded accordingly. Some sold their possessions, reasoning that wealth was meaningless if the world was ending. Some abandoned long-term plans entirely. Some made desperate appeals to their gods because divine intervention seemed like the only force capable of operating at the scale of what they were witnessing. These were not irrational responses. They were the logical conclusions of people trying to make sense of an unprecedented event using the only frameworks available to them, frameworks that had no category for stratospheric aerosols or volcanic sulfur chemistry, only for divine wrath and cosmic disorder. What emerges from this chorus of witnesses, Byzantine, Chinese, Irish, Syrian, each speaking from a different corner of the 6th century world, is not a single dramatic story, but a quiet, accumulating weight of testimony. No one source proves what happened. But taken together, cross-referenced with the sulfate layers sealed in polar ice, they form a picture that is difficult to dismiss. Something dimmed the sun across the entire planet for more than a year. Something disrupted growing seasons from Constantinople to China. Something broke the agricultural rhythms that human civilizations had depended on for millennia. The witnesses recorded what they saw each in their own language of dread and bewilderment, but none of them could explain it. None of them knew that the answer was not in the heavens but in the earth, locked in the magma chambers of volcanoes they had never heard of on continents some of them did not know existed. What the trees remember. A bristlecone pine growing in the White Mountains of eastern California can live for more than 4,000 years. It adds one ring of growth each year, a band of new wood laid down between the old heartwood and the bark, its width determined by the conditions of that particular growing season. In warm years, with adequate moisture, the ring is wide. In cold years or years of drought, the ring compresses to a thin, barely visible line. Each tree, then, is a kind of archive not of events or intentions, but of climate itself, recorded in the patient language of cellulose and annual growth. When dendrochronologists began examining bristlecone pines and cross-referencing their rings with those of European oaks, Siberian larches, and preserved logs pulled from Irish bogs, they found something in the mid-6th century that stopped them. The rings dated to 536 AD, were among the narrowest in the entire record, not just in one species or one region, but simultaneously across the northern hemisphere in trees separated by thousands of miles of ocean and continent. The science behind this reading is more precise than most people realize. Dendrochronology does not simply count rings and guess at dates. It builds continuous overlapping chronologies by matching the ring patterns of living trees with those of older dead wood, then matching those with even older timber preserved in archaeological sites or waterlogged soils. By the early 2000s, researchers had constructed unbroken tree ring sequences stretching back several millennia from multiple locations worldwide. These sequences could be dated to the exact calendar year, and when the line for 536 appeared in chronology after chronology from the Alps to Scandinavia to the American Southwest, the picture was unmistakable. Trees that had weathered centuries of ordinary variation in rainfall and temperature suddenly showed growth suppression so severe that some rings were barely visible under magnification. Whatever had dimmed the sun and chilled the summers described by Procopius and the Chinese astronomers had also been felt by organisms with no capacity for exaggeration or political motive. The trees simply recorded what happened to the light and the warmth, and what happened was a near cessation of normal growth for multiple consecutive years. The detail that distinguishes this event from ordinary cold snaps or regional droughts is the synchronization. A harsh winter in northern Europe might suppress growth in Scandinavian pines without affecting trees in the Mediterranean or North America. A drought in California might stress bristlecone pines, while oaks in Ireland grow normally. But the 536 signal appears everywhere at once in species adapted to vastly different climates, rooted in different soils, drawing water from different sources. European oaks and Siberian larches show the same sudden narrowing. Bristlecone pines in California and kauri trees in New Zealand both register the shock. This global synchronization is the fingerprint of a stratospheric event, something that affected not regional weather, but the total amount of sunlight reaching the Earth's surface. No local drought and no regional cold front, no ordinary fluctuation in ocean currents could produce this pattern. Only something suspended in the upper atmosphere, intercepting sunlight before it reached any particular latitude or longitude, could suppress tree growth across such disparate ecosystems simultaneously. The tree rings also revealed something the ice cores could not, a timeline of recovery, or rather the agonizing lack of one. After the initial crash in 536, there was a slight rebound in 537 and 538 rings, widened marginally, suggesting that temperatures had begun creeping back toward normal as the first pulse of volcanic aerosol started to settle out of the stratosphere. But then around 540 or 541, the rings narrowed again sharply in many of the same chronologies. This second crash corresponds precisely with the second sulfate spike found in the ice core's evidence of another major eruption reloading the atmosphere with the light-blocking aerosols, just as the first veil was beginning to thin. The trees recorded what amounted to a false recovery, a brief respite followed by a renewed plunge into cold and darkness. For any farmer watching a field of grain begin to grow again after 2 failed seasons, only to see frost return in midsummer and kill the young shoots a second time, the psychological impact would have been devastating. The trees do not record despair, but they record the conditions that would have produced it. In some regions, normal growth patterns did not return for more than a decade. Scandinavian pines show suppressed rings through the 540s and into the early 550s. Some high-altitude bristlecone pines in the American West exhibit what dendrochronologists call frost rings, not merely narrow growth bands, but rings that show cellular damage from freezing during what should have been the growing season. These frost rings are rare in the multi-thousand-year bristlecone record. Their appearance in the 536-545 period places that decade among the most climatically extreme intervals in the entire Holocene, the 11,000-year epoch of relative warmth and stability, during which all of human civilization developed. The trees in their quiet way are saying that the world crossed a threshold, during those years entering a cold regime that had no precedent in the lived experience of any human culture on the planet. What makes this evidence so compelling is its independence. The ice cores record atmospheric chemistry. The written sources record human observation and suffering. The tree rings record biological response, the simple, measurable reality of how much a living organism could grow in a given year. 3 entirely separate lines of evidence preserved in 3 entirely different media, all converging on the same years, the same severity, the same global reach. No single line of evidence would be conclusive on its own. Together they form something difficult to set aside. And yet for all their convergence, none of them could answer the question that mattered most to the people who lived through it. Not what had happened in the atmosphere, but what was about to happen on the ground, in the fields and cities and trade routes, where the consequences of a dimmed sun would unfold with a slowness that made them all the more difficult to survive. The fingerprint in the glass. What does it take to identify a volcano that erupted 1,500 years ago, when no living witness understood what a volcano was capable of doing to the global atmosphere? The ice cores had confirmed the timing and the scale. The tree rings had mapped the biological damage. The written sources had recorded the human experience, but none of these could point to a specific mountain, a specific magma chamber, a specific place on the map where the Earth had torn itself open and filled the sky with sulfur. To answer that question, scientists had to turn to a discipline that resembles forensic investigation more than it resembles traditional geology: geochemical fingerprinting, the painstaking process of extracting microscopic particles from ancient ice and matching their chemical signatures to known volcanic sources scattered across the planet. The principle is straightforward, even if the execution is extraordinarily difficult. Every volcanic system has a unique chemical identity determined by the composition of the magma that feeds it. The ratios of certain isotopes, strontium, neodymium, lead vary from volcano to volcano based on the age and composition of the underlying crustal rock. Trace elements like barium, zirconium, and titanium appear in different proportions depending on the specific conditions under which the magma formed. And when an eruption is violent enough to shatter molten rock into microscopic shards of volcanic glass, those shards carry the chemical fingerprint of their source, like fragments of a signature legible under the right instruments. The challenge is finding them. In an ice core layer representing a single year, the volcanic particles are measured in parts per billion, invisible to the naked eye, detectable only through mass spectrometry and electron microscopy, and easily contaminated by even the slightest mishandling of samples. Laboratories working on this problem operate under conditions closer to a surgical theatre than a traditional geology department. Through the 2010s, multiple research teams converged on a candidate that surprised many in the field. The chemical fingerprint extracted from the 536 ice core layer did not match Icelandic volcanic systems, which had been a leading hypothesis for years given Iceland's prolific eruption history and its proximity to the Greenland ice sheet where the cores were drilled. Nor did it match Mediterranean sources like Vesuvius or the volcanic systems of the Aegean. Instead, the isotope ratios and trace element compositions pointed southward toward a tropical source, a volcano near the equator where eruptions would have maximum global impact, because stratospheric winds at tropical latitudes distribute aerosols into both hemispheres simultaneously. The leading candidate that emerged was Ilopango, a massive volcanic complex in what is now El Salvador, sitting in the highlands of Central America, with a crater lake 4 miles across the scar of an eruption, so violent it had deposited ash layers meters thick over 1,000 square miles of surrounding terrain. Ilopango had long been known to volcanologists as the source of one of the most powerful eruptions in Central American history, an event called the Tierra Blanca Joven. The explosion had been catastrophic on a regional scale, depopulating Maya territories across a wide radius, burying entire landscapes under pyroclastic deposits, and leaving the area uninhabitable for decades. But dating the eruption precisely had always been difficult. Radiocarbon analysis of charcoal buried in the ash deposits yielded wide ranges somewhere between 400 and 600 AD a window, too broad to connect the eruption definitively to the 536 atmospheric event. When researchers compared the geochemical signature of Ilopango's ash with the volcanic glass shards extracted from the 536 ice core layer, however, they found what they described as a compelling match isotope ratios that aligned trace element compositions that were consistent glass shard morphologies that fit the profile. Supporting evidence arrived from lake sediments in Central America, which showed massive erosion and flooding events in the late 500s and 30s, exactly the kind of landscape disruption you would expect after a major eruption stripped vegetation from hillsides and destabilized watersheds across the region. Yet the identification remains debated, and it is worth pausing here to acknowledge the uncertainty honestly. Some researchers have proposed that the Tierra Blanca Joven eruption may have occurred earlier than 536, perhaps as early as the 430s, based on revised radiocarbon calibrations and archaeological evidence from Maya sites that seem to show abandonment horizons predating the mid-6th century. Others argue that the geochemical match, while compelling, is not yet definitive, that the number of analysed glass shards is small, that some trace element ratios fall within ranges shared by other tropical volcanic systems, and that more sampling is needed before Ilopango can be confirmed rather than merely suspected. The honest scientific position as of the most recent published work is that Ilopango is the strongest candidate for the 536 eruption, but not yet a closed case. The fingerprint fits, but the jury has not returned a final verdict. What is less debated is what the eruption, wherever it originated, would have done to the atmosphere. Estimates based on the ice core sulfate concentration suggest that the initial 536 event injected somewhere between 50 and 100 million tons of sulfur dioxide into the stratosphere. At that scale, the sulfur would have converted rapidly into a global aerosol veil capable of reflecting 5 to 10% of incoming solar radiation back into space. The arithmetic of what follows is precise and unforgiving. A sustained reduction of even 2 to 3% in solar input translates to a global temperature depression of roughly half a degree Celsius, enough to shorten growing seasons, shift frost lines, and stress agricultural systems across entire continents. At 5 to 10% reduction sustained over multiple years, and compounded by subsequent eruptions in 540 and 547, the cooling enters a range of 1.5 to 3 degrees Celsius, comparable to the temperature difference between our current climate and the coldest centuries of the Little Ice Age, compressed not into a slow, centuries-long drift, but into a sudden, inescapable plunge. The chemical detective work that traced the 536 eruption from ice core to candidate volcano represents one of the most remarkable feats of interdisciplinary science in recent decades. Glaciology, geochemistry, volcanology, and archaeology converging on a single question across multiple continents and laboratories. But for the people who lived through the event, none of this mattered. They could not analyze isotope ratios or measure sulfate concentrations. They knew only that the sky had changed, that the light was wrong, that the warmth they depended on had withdrawn without explanation. And as the first failed harvest gave way to a second, and the second to a third, the consequences began moving from the atmosphere into the fields, the granaries and the cities, from chemistry into human suffering, from a veil of sulfuric acid too thin to see into a famine too vast to escape. The dominoes in the fields. The transition from atmospheric chemistry to human catastrophe did not announce itself with a single dramatic moment. It arrived in the fields quietly at first, in the form of seedlings that sprouted but failed to thrive grain stalks, that reached for a sun that could not nourish them, growing seasons that compressed week by week until the arithmetic of agriculture simply stopped working. Photosynthesis is not a flexible process. It requires a threshold of solar energy to convert carbon dioxide and water into the sugars that sustain plant growth, and when incoming light drops below that threshold, plants do not merely grow slowly, they cannot produce the energy they need to survive. In the perpetual twilight described by Procopius and the Chinese chroniclers, crops across the northern hemisphere were not struggling. They were starving just as surely as the people who depended on them would soon be starving too. The cruel precision of the failure lay in its completeness. In ordinary bad years, years of regional drought, localized flooding, unseasonable frost, farmers could expect to salvage something. A half harvest, a quarter harvest, enough to scrape through the winter if they rationed carefully and supplemented with stored grain from better years. But the accounts from 536 and the years that followed describe something different in kind, not merely in degree. In many regions, farmers harvested nothing at all. The Irish Annals spare phrase, "a failure of bread," conceals the totality of that collapse. Not a reduced yield, but an absence, a season in which the fundamental transaction between seed and soil and sunlight simply did not occur. And because the dimming persisted through the following year and into the year after that, the failure was not a single event that communities could absorb and recover from. It was a cascading sequence in which each failed season made the next one worse. Each depleted granary reduced the margin for survival, and each month of hunger weakened the bodies and the social structures that might otherwise have organized a response. The mathematics of pre-industrial agriculture made this cascade almost inevitable. Most grain crops, wheat, barley, millet, the staples that fed the 6th century world, require between 90 and 120 days from planting to harvest. They need not only adequate sunlight, but a frost-free window long enough to complete their growth cycle. When the volcanic aerosols suppressed summer temperatures by 2 to 3 degrees, Celsius, the frost-free period in many northern regions, shrank below that critical threshold. Fields that had been reliably agricultural for centuries suddenly could not support a full growing cycle. Farmers were not dealing with a poor harvest. They were dealing with the disappearance of the conditions that made harvesting possible at all. The distinction matters because it determined what came next. A poor harvest depletes food stores. The elimination of the growing season depletes everything food seed grain saved for next year's planting confidence that the pattern of seasons can be trusted, and ultimately the social contract between rulers and ruled that depends on the basic promise that the system will provide. By the autumn of 536 communities across the Northern Hemisphere were entering a crisis that had no precedent in living memory. Grain reserves, where they existed at all, had been designed to bridge a single bad winter, not to sustain populations through an indefinite suspension of agriculture. And in the 6th century, those reserves were not distributed equitably. Political power in most societies meant control of food supplies, and when the harvest failed, the powerful hoarded what remained. Wealthy landowners secured their granaries. Military commanders requisitioned food for their armies. Religious institutions controlled their own stores, distributing them strategically to maintain loyalty and influence. For ordinary farmers and labourers, the people who had actually grown the food, there was nothing. The social hierarchy that had functioned tolerably in times of surplus became a death sentence in times of scarcity, channeling the remaining food upward, while those at the bottom were left to find alternatives that grew increasingly desperate as the months wore on. The Chinese chronicles describe people eating tree bark and boiling grass into soup. When the bark was exhausted, they turned to things the chroniclers recorded, but clearly found difficult to write about. In the Mediterranean sources describe urban populations fleeing cities that could no longer feed them. Constantinople, Antioch, Alexandria, all dependent on grain imports from agricultural hinterlands that were themselves failing. The supply chains that had connected producers to consumers across hundreds of miles of land and sea simply ceased to function, not because the infrastructure had been destroyed, but because there was nothing to transport. Ships designed to carry Egyptian grain to Constantinople sat idle because there was no grain to carry. Roads built to move agricultural surplus to urban markets carried only refugees moving in the opposite direction, fleeing cities in search of food that the countryside no longer had. The collapse of lead pollution recorded in Greenland ice cores during this period tells the same story from a different angle. Lead in the ancient atmosphere came primarily from silver mining and smelting, and when the lead signature drops to near zero, it means the entire economic system that supported mining trade and monetary exchange had ceased to function. People cannot eat silver, and when survival becomes the only priority, the elaborate economic structures that civilizations depend on simply stop. What followed the agricultural collapse was not a single catastrophe, but a series of interlocking failures, each one creating conditions for the next. Famine weakened immune systems. Weakened populations became vulnerable to diseases that would have been manageable in healthier times. Social breakdown disrupted sanitation, medical care, and the organised responses that might have contained outbreaks. Mass migration as people fled failed agricultural regions in search of food, brought populations into contact with new disease environments, and created crowded and sanitary conditions in cities and refugee settlements. And into this landscape of accumulated vulnerability 5 years after the sun first dimmed, something emerged from the rodent populations of East Africa or Central Asia that would transform the crisis from a catastrophe into an extinction-level event for entire civilizations. But that belongs to the next chapter. For now, the fields lay empty, the granaries were bare, and across the northern hemisphere, millions of people were learning what it meant to live in a world where the most basic assumption of agricultural life, that the seasons would return, that the sun would nourish what was planted, that the earth would provide, had quietly and inexplicably ceased to be true. What the evidence does not say not. Every scientist who has studied the 536 event agrees on what it means, and it would be dishonest to move forward without acknowledging the places where the evidence thins, where the narrative that connects volcanic eruption to civilizational collapse relies on inference rather than proof, and where reasonable scholars looking at the same data have reached different conclusions. The story told so far sulfate in ice, narrow rings in trees' dimmed sun. In historical accounts, failed harvest cascading into famine has a compelling internal logic. Each piece of evidence reinforces the others, but coherence is not the same as certainty, and the history of science is full of elegant stories that turned out to be incomplete, or that mistook correlation for causation, or that simplified a complex reality into a chain of dominoes that was tidier than the truth. The first point of honest uncertainty concerns the identification of the volcano itself. Ilopango remains the leading candidate for the 536 eruption, and the geochemical evidence linking its ash to particles found in the ice core is by the standards of the field strong. But strong is not conclusive. Some volcanologists have pointed out that the radiocarbon dating of the Tierra Blanca Joven eruption, the massive explosion that created Ilopango's crater lake, yields a range broad enough to accommodate dates well before 536. A revised calibration published in recent years suggested the eruption may have occurred as early as the 400s and 30s, which would place it a full century before the atmospheric event recorded in the ice. If that dating is correct, then the geochemical match between Ilopango ash and the 536 ice layer becomes coincidental rather than causal, two signatures that resemble each other, but belong to different events. The counter-argument is that the revised dating relies on a small number of samples, and that the archaeological evidence from Maya sites in the eruption zone is ambiguous enough to support either timeline. But the disagreement is real, and the identification of Ilopango as the 536 source should be understood as a working hypothesis, not a settled fact. The second uncertainty is broader, and in some ways more consequential. The narrative of cascading collapse eruption leading to dimming leading to crop failure leading to famine leading to plague is powerful, precisely because it is sequential and logical. Each step follows from the one before. But the civilizations that collapsed during this period were not simple systems with single points of failure. Teotihuacan, the great Mesoamerican metropolis that was burned and abandoned around the mid-6th century, had been experiencing internal political tensions for decades before the climate crisis. Archaeological evidence suggests factional conflict shifts in trade patterns and possible challenges to the authority of its ruling elite, all processes that were well underway before any volcanic aerosol reached the stratosphere. The climate disruption may have been the final stress that broke an already fracturing system, or it may have been one factor among several, or its role may have been smaller than the timing suggests. The honest answer is that we cannot fully disentangle the contributions. Similarly, the Sassanid Persian Empire's long decline involved military overextension, costly wars with Byzantium, and internal religious conflicts that had nothing to do with volcanic winter. To attribute its eventual fall to Arab armies in the 600s primarily to vulnerabilities created by the 536 event requires a chain of causation stretching across nearly a century. Plausible perhaps, but difficult to demonstrate with the kind of evidence that would satisfy a skeptic. The third area of uncertainty concerns the Justinianic plague and its relationship to the volcanic winter. The argument that climate disruption created the conditions for plague emergence is epidemiologically reasonable. Famine does weaken immune systems, social breakdown does degrade sanitation, ecological disruption does force rodent populations into closer contact with humans. But the specific mechanism by which Yersinia pestis moved from its reservoir in wild rodent populations to the grain ships of the Mediterranean has never been directly demonstrated for the 6th century. It is an inference drawn from modern understanding of plague ecology, applied retrospectively to a period for which we have limited evidence. Some historians have argued that the plague's arrival in the Mediterranean may have been largely independent of the climate crisis, that the bacterium was already spreading along trade routes, and would have reached Constantinople regardless of whether the harvests had failed. The timing may be coincidental rather than causal. The honest position is that the connection is plausible and supported by epidemiological theory, but it has not been proven in the way that the ice core chemistry or the tree ring synchronization has been proven. And there is the matter of the mortality figures themselves. Estimates that the combined death toll from famine and plague reached 50 million, or possibly 100 million across Eurasia, are sometimes cited as though they represent measured data. They do not. They are extrapolations from fragmentary evidence, a passage in Procopius claiming 10,000 deaths per day in Constantinople, tax records showing declining household registrations in China pollen, data suggesting agricultural abandonment across wide areas. Each of these data points carries its own uncertainties, and when they are combined into aggregate estimates, the uncertainties multiply rather than cancel. The true death toll of the 536 crisis and its aftermath is in a strict sense unknowable. It was certainly enormous. It may have been among the greatest demographic catastrophes in human history. But the specific numbers should be held lightly as approximations rather than facts. None of this diminishes the reality of what happened. The sulfate is in the ice. The narrow rings are in the trees. The accounts of dimmed sun and failed harvests are in the manuscripts. The mass graves are in the ground. The evidence for a profound multi-year climate disruption beginning in 536 is as strong as evidence for any event in the pre-modern world. What is less certain is the precise chain of consequences which collapses were caused by the climate crisis, which were merely accelerated by it and which might have happened regardless. The pattern is there. The connections are suggestive. The discomfort is that suggestive is not the same as certain, and the distance between the two is where honest inquiry lives. It may be that the volcanic winter of 536 was the single thread that when pulled unravelled half a dozen civilizations. It may be that it was one force among many arriving at a moment when multiple systems were already under stress. The evidence does not quite let us choose, and perhaps the most responsible thing we can do is hold both possibilities open as we move forward into the cities, the trade routes and the plague ships, where the next chapter of this story unfolds. The bacterium in the hold. A single flea can carry roughly 2,000 cells of Yersinia pestis in its gut. The bacterium colonizes the flea's digestive tract, forming a biofilm that eventually blocks the insect's ability to feed normally. The flea, unable to swallow blood efficiently, bites more frequently and more desperately, regurgitating bacteria into each new wound as it tries to clear the blockage. It is a small mechanism, microscopic, silent, invisible to the naked eye, and yet it is the engine that drove one of the deadliest pandemics in human history. Somewhere around 541 AD, 5 years after the sun first dimmed and the harvest began failing, this mechanism found its way from the rodent populations where it had quietly cycled for centuries into the grain stores, the ships and the cities of the Mediterranean world, and everything that the volcanic winter had weakened the plague would break. The first recorded outbreak appeared in Pelusium, a port city on the Mediterranean coast of Egypt. The location was not accidental. Pelusium sat at the mouth of one of the Nile's eastern distributaries, a nexus of trade routes connecting the Egyptian interior with the broader Mediterranean shipping network. Grain from the Egyptian harvest, when there was a harvest, passed through ports like Pelusium on its way to Constantinople, Antioch, and cities throughout the Eastern Roman Empire. The ships that carried that grain also carried rats, and the rats carried fleas, and the fleas carried Yersinia pestis. Within months of the initial outbreak at Pelusium, the plague had reached Alexandria, Egypt's largest city, and the central hub of the imperial grain trade. From Alexandria, it had access to every port the empire's merchant fleet could reach. The disease did not spread by air or water or divine wrath. The contemporary observers would propose all three explanations. It spread by commerce, by the same networks of exchange that had connected the Mediterranean world for centuries, now repurposed as vectors for a pathogen that could not have designed a more efficient distribution system if it had tried. The historian Procopius, who had already recorded the dimming of the sun with such careful precision, now found himself documenting something far more immediate and personal. He was in Constantinople when the plague arrived in 542, and his account carries the weight of a man describing horrors he witnessed with his own eyes, rather than heard about second-hand. The disease began with sudden fever, he wrote. Victims felt hot but not alarmingly ill at first, and many expected to recover. Then the real symptoms appeared. Swollen lymph nodes erupted in the groin, the armpits, the neck growing in some cases to the size of a grapefruit. The buboes turned black as tissue died. Some burst releasing fluid. Others simply continued growing until the body could no longer sustain itself. Delirium followed in many cases, hallucinations, violent episodes, comas from which patients never woke. The speed was what terrified observers most. A person could appear healthy at dawn and be dead by nightfall with no pattern or predictability to determine who would survive and who would not. Modern genetic analysis has confirmed what Procopius was describing. DNA, extracted from 6th century burial sites across the Mediterranean, has identified the pathogen as Yersinia pestis, the same species that would cause the Black Death 800 years later, though a different strain and earlier branch on the plague's evolutionary tree. The genetic evidence reveals something else that the written sources could not. This was not a single introduction event. Multiple strains of the bacterium have been recovered from different burial sites, suggesting that the plague entered the Mediterranean world through several independent pathways, likely carried by different rodent populations along different trade routes. The disease had established itself broadly not as a single outbreak radiating from one point, but as a diffuse invasion arriving from multiple directions, a pattern consistent with the widespread ecological disruption that years of climate stress had created across the rodent habitats of Africa and Central Asia. Constantinople, with its 500,000 inhabitants crowded within defensive walls, became the pandemic's most devastating theatre. The city's population was already weakened by years of food shortages. The grain shipments from Egypt had been unreliable since the harvest began failing, and malnutrition had compromised immune systems across all social classes. When the plague arrived on the same ships that brought whatever grain remained, it found a population with diminished biological defences, living in dense urban conditions with sanitation systems already strained by years of crisis. Procopius claimed that at the epidemic's peak 10,000 people were dying each day in the capital. Modern historians generally regard this figure as an exaggeration, but the archaeological evidence from mass burial sites suggests that the true mortality, whatever the precise number, was staggering. Bodies were stacked in towers stuffed into the walls of fortifications, loaded onto ships, and towed into open water to be sunk. The systems that civilized societies maintain for handling death, the rituals, the burial grounds, the dignity afforded to the departed, collapsed under a volume of dying that no system had been designed to accommodate. Emperor Justinian himself contracted the plague and nearly died. He survived, but the empire's trajectory did not. The ambitious campaigns to reconquer the Western Roman territories, already stalled by years of famine and supply chain failure, were effectively abandoned. Armies that had been depleted by desertion and hunger were now decimated by disease. Tax revenues collapsed as the population that generated them disappeared. The administrative machinery that had held the empire together through the initial years of climate crisis continued to function, but it was governing a diminished realm, fewer people, less wealth, less capacity to project power or maintain the infrastructure that distinguished Roman civilization from the fragmented kingdoms emerging in the West. The plague did not destroy the Eastern Roman Empire outright. It did something perhaps more insidious. It removed the margin, the surplus of population and wealth and energy that had allowed the empire to absorb previous shocks and recover. From 542 onward, the empire would survive, but it would never again possess the resources to do more than survive. And the plague did not strike once and withdraw. The first wave subsided by 544, but it returned in 558, then again in 573, again in 599, recurring every 15 to 20 years, for the next 2 centuries, each wave arriving just as populations had begun to stabilize each resurgence, preventing the full demographic recovery that might have restored the empire's strength. The pattern suggests that Yersinia pestis had become endemic, established in permanent reservoirs within rodent populations across the Mediterranean and beyond, spilling over into human communities whenever conditions aligned, when rat populations surged, when flea activity increased, when human defenses were low. For generations, the plague was not an event, but a condition, a recurring feature of life that shaped everything from economic planning to theological interpretation to the basic question of whether it was worth planting crops that you might not live to harvest. The volcanic winter had dimmed the sun. The famine had emptied the fields, and now the plague was emptying the cities not all at once but in waves, each one smaller than the last but arriving before the damage of the previous wave had healed, like a wound reopened before the scars fully formed. Empires on their knees, In the spring of 540, Justinian's general Belisarius rode into Ravenna at the head of a Roman army and accepted the surrender of the Ostrogothic king. It was supposed to be the culmination of years of planning the reconquest of Italy, the restoration of Roman authority over territories that had been lost for more than half a century. The Hagia Sophia was nearing completion in Constantinople. Its dome an architectural declaration that Roman civilization had not merely survived, but was ascending toward a new golden age. The empire controlled North Africa, held the eastern Mediterranean, and was now reclaiming the Italian peninsula. For a brief moment, the dream of a restored Rome seemed not just possible but inevitable. Within 2 years, that dream would be functionally dead, not killed by a rival army or a political revolution, but by a combination of empty granaries, depleted treasuries, and a plague that would remove a third of the empire's population before the decade was out. The Gothic War in Italy illustrates the mechanism of collapse with painful clarity. What had been planned as a swift campaign of reconquest became a 20-year grinding catastrophe that devastated the very lands it was meant to reclaim. The problem was not military strategy, but logistics, the fundamental inability to feed supply and pay an army, when the agricultural base that supported all three was failing simultaneously. Soldiers who were not fed deserted. Local populations who were forced to feed occupying garrisons when they could barely feed themselves turned hostile. Supply lines that depended on regular grain shipments from North Africa and Egypt became unreliable as those regions struggled with their own harvest failures. By the time the war finally ended in 554, Italy had been so thoroughly depopulated and economically ruined that the reconquest was essentially meaningless. Rome had reclaimed a wasteland. The aqueducts that had supplied the city's water for centuries fell into disrepair because there were not enough people left to maintain them. The population of the city of Rome itself, which had once numbered over 1 million, may have fallen below 30,000. The empire had won the war and inherited ruins, but Byzantium, for all its suffering, did not collapse entirely, and the reasons why tell us something important about what makes complex societies resilient under catastrophic stress. The Eastern Roman Empire possessed something that many of its contemporaries lacked: redundancy. Its agricultural base was not concentrated in a single region, but distributed across multiple climate zones: Egypt, Anatolia, the Balkans, parts of the Levant. When one region's harvest failed, others might still produce something. The empire could shift resources, however imperfectly, from surplus areas to deficit areas through an administrative system staffed by professional bureaucrats who kept written records and could coordinate emergency responses, even when political leadership was incapacitated. When Justinian fell ill with the plague in 542 and was unable to govern for weeks, the imperial administration continued to function, collecting taxes, distributing food, paying the military, because the systems did not depend on a single person's continued health. This institutional depth was not glamorous, but it was the difference between survival and extinction. 6,000 miles to the east, the Sassanid Persian Empire was discovering what happened when that kind of redundancy was absent. The Sassanids controlled some of the most productive agricultural land on earth. The Tigris and Euphrates river valleys, the ancient breadbasket of Mesopotamia, irrigated by canal systems that had functioned since Sumerian times. In normal conditions, this was an extraordinary advantage. But Mesopotamian irrigation was a system that required constant organised labour to maintain. Canals had to be dredged, flood damage had to be repaired, water flow had to be carefully managed to prevent the salinisation that could render fertile land permanently barren. When the population began declining, first from famine as the climate crisis reduced yields, then from plague as the pandemic spread eastward along trade routes, the labour force that maintained the irrigation infrastructure shrank below the critical threshold. Canals silted up, flood control systems failed. Agricultural land was lost not to a single catastrophe, but to a slow, irreversible degradation as the maintenance that had kept the system productive for millennia simply stopped being performed. Each year the empire could feed fewer people, which meant even less labour for maintenance, which meant even more land lost a spiral of decline that the Sassanid political system, centralised and dependent on agricultural surplus from specific regions, could not arrest. The Silk Road trade that had enriched the Sassanid Empire for centuries was collapsing in parallel. The great overland route connecting China to the Mediterranean depended on a chain of oasis cities across Central Asia waypoints where caravans could rest, resupply and exchange goods. These oasis cities were themselves dependent on delicate water sources vulnerable to climate disruption. As the volcanic winter altered precipitation patterns across Central Asia, some of these water sources diminished or failed. Caravans that had once moved Chinese silk westward and Roman gold eastward found fewer functioning stops along the route. Trade volumes declined. The transit taxes that had been a major source of Sassanid revenue dried up alongside the oases. Cities that had prospered as commercial hubs withered into villages. The merchants who had facilitated not just trade but communication between distant regions of the empire disappeared, and with them went the connective tissue that had held Sassanid territories together as a functioning whole rather than a collection of isolated provinces. The contrast between Byzantine resilience and Sassanid fragility was not a matter of superior culture or greater virtue. It was structural, a consequence of geography, administrative design, and the specific vulnerabilities built into each empire's economic foundation. Byzantium had multiple breadbaskets and a professional bureaucracy capable of managing crisis across distributed territories. The Sassanids had concentrated their agricultural productivity in a system that was magnificently efficient under normal conditions, but catastrophically fragile when those conditions changed. Both empires were hit by the same volcanic winter, the same temperature depression, the same cascade of famine and plague. One bent and held. The other developed fractures that would widen over the following century until, when Arab armies arrived in the 600s, the empire that had seemed invincible shattered in less than 2 decades. The volcanic winter had not destroyed the Sassanid Empire directly. It had removed the resilience, the surplus, the redundancy, the margin for error that would have been needed to withstand the next challenge. And the next challenge, when it came, found an empire already hollowed from within by a century of compounding loss. The cities that burned themselves. Along the Avenue of the Dead in what is now central Mexico, the stone walls of pyramids and temple platforms still bear the scorch marks of fires that were set not by invaders, but by the people who built them. The burn patterns are concentrated, focused on ceremonial structures and elite residences, rather than distributed randomly across the urban landscape. This is not the archaeological signature of an accidental fire or an external military attack. It is the signature of deliberate targeted destruction, directed at the symbols of authority by a population that had lost faith in the system those symbols represented. Teotihuacan, the place of the gods, home to more than 100,000 people in the early 6th century, one of the largest cities on earth at the time, was not conquered. It was repudiated by its own inhabitants, burned, abandoned, and left to stand empty for 1,000 years, until the Aztecs found its ruins and gave it the name it carries today. The timing of Teotihuacan's collapse has been debated by archaeologists for decades, with proposed dates ranging across a span of several generations in the 6th and 7th centuries. But the convergence with the volcanic winter of 536 is difficult to dismiss. The city sat in a highland valley with limited arable land dependent on intensive agricultural techniques that required consistent rainfall and predictable growing seasons to feed a population far larger than the immediate landscape could naturally support. Teotihuacan had solved this problem brilliantly for centuries, developing irrigation systems, managing chinampas, organizing labor with sufficient precision to generate the surplus that sustained not just the city's population, but its monumental architecture, its craft specialists, its merchant network stretching from the American Southwest to the Maya lowlands. But the solution was optimized for the climate that had prevailed during the city's centuries of growth. When that climate shifted, when rainfall patterns changed, when growing seasons shortened, when the temperatures described in tree ring records and ice core chemistry arrived in the highland valleys of central Mexico, the optimization became a trap. There was no slack in the system, no alternative breadbasket to draw from, no maritime trade network capable of importing bulk grain from distant regions. Mesoamerican civilizations lacked draft animals for long-distance overland transport and had no tradition of ocean-going cargo vessels. When the local harvest failed, the city could not be fed from elsewhere. The population was stranded in a metropolis that had become almost overnight unsustainable. What happened next follows a logic that archaeologists recognize from collapse events across many cultures and periods. When a political and religious system fails to deliver the basic conditions it has implicitly promised, when the rains do not come, when the harvests do not materialize, when the ceremonies performed in the great temples produce no visible result, the legitimacy of that system erodes. The burning of Teotihuacan's ceremonial center was not random violence. It was a focused rejection of the authority structures that had organized the city's life for generations. The temples where priests had performed rituals meant to ensure agricultural fertility were targeted precisely because those rituals had failed. The elite residences where rulers had lived in comfort while ordinary people went hungry were burned precisely because the social contract they represented surplus in exchange for obedience had been broken by conditions no ritual or ruler could control. The people of Teotihuacan could not know that a volcanic eruption in Central America or elsewhere had disrupted the global climate. They could only know that the gods had stopped answering, and that the priests who claimed to speak for those gods had nothing to offer a starving city. Far to the east and north across the vast grasslands stretching from Hungary to Mongolia, a different kind of collapse was producing a different kind of consequence. The steppe nomads, Turkic Mongolic and other pastoralist peoples who herded horses, sheep and cattle across thousands of miles of open grassland, were among the populations most immediately vulnerable to climate disruption, though their vulnerability expressed itself not as urban collapse but as mass migration. Nomadic pastoralism depends on an intimate knowledge of seasonal patterns, where grass will grow at what time of year, where water sources will be available, which routes to follow as seasons change. This knowledge accumulated over generations and transmitted orally from elders to children constituted an extraordinarily sophisticated adaptation to one of the Earth's most demanding environments. But it was an adaptation calibrated to a specific climate regime, and when that regime shifted, the knowledge became unreliable. Pastures that had been green in May were brown and dead. Water sources that had been dependable for generations diminished or vanished. Herds that represented not just wealth, but survival began dying as the grasslands failed to regenerate on their accustomed schedule. The nomads' response was the only one available to people whose survival depends on mobility. They moved, but they did not move randomly. They moved toward regions that still had resources, which meant increasingly toward the settled agricultural lands to their south and west. The Avars, a confederation of Turkic-speaking peoples, appeared suddenly in European historical sources in the 500s, invading the Balkans and pressing against the borders of an already weakened Byzantine Empire. They had come from the eastern steppe, driven westward by a chain of displacement that began when climate failure in their home territories made their traditional way of life impossible. The Gökturks emerged during the same period, building a vast empire across Central Asia, not merely as conquerors but as political innovators, creating administrative structures capable of managing resources across enormous territories where local conditions had become unpredictable. These migrations were not the random wanderings of primitive peoples. They were strategic responses to ecological catastrophe, undertaken by societies that understood their environment with extraordinary precision and recognized before anyone else that the environment had fundamentally changed. The pattern that emerges from Teotihuacan's ashes and the steppe migrations is the same pattern visible in the Sassanid decline and the Byzantine contraction, a global system of interconnected consequences flowing from a single atmospheric event. But the specific form of each civilization's response was shaped by its particular geography, social organization, and the vulnerabilities embedded in its way of life. Teotihuacan, dense and immobile, turned inward and destroyed itself. The steppe nomads, mobile and adaptive, turned outward and reshaped the political map of Eurasia for centuries to come. Byzantium, complex and bureaucratic, contracted but held. Each response was rational within its own context, each was driven by the same underlying cause, and each would produce consequences that outlasted the volcanic winter itself by generations. The dust was settling from the stratosphere at last, but the human reverberations of its passage were only beginning to be felt, rippling outward into decades and centuries that would look nothing like the world that had existed before the sky went dim. The long silence. A pollen core extracted from the sediment of a lake in southern Sweden tells a story that no human chronicler thought to record. In the layers dated to the early 6th century, the pollen of cultivated grains, wheat, barley, rye appears in steady, predictable concentrations, the signature of an agricultural landscape maintained by generations of farmers who cleared forest-tilled soil and planted crops in seasonal rhythms so consistent they left a legible chemical record at the bottom of a body of water. Then in the layers corresponding to the late 500s and 30s and 500s and 40s, the grain pollen drops sharply. In its place, the pollen of birch, hazel and wild grasses surge as pioneer species, the first plants to reclaim land when human cultivation ceases. The forest was returning, the farms were being abandoned, and the abandonment was not temporary. In some Swedish pollen records, agricultural indicators do not recover to pre-536 levels for more than 150 years. The land itself was recording an absence not of sunlight this time, but of people. This pattern repeats across Northern Europe with a consistency that is quietly devastating. In Norway, pollen records show similar agricultural retreat, beginning in the late 500s and 30s. In Ireland, bog sediments reveal declining cereal cultivation through the mid-6th century. In parts of Britain, the archaeological record shows settlements that had been continuously occupied since before the Roman period, finally going dark, not destroyed by violence but simply emptied, their inhabitants gone to places the evidence cannot follow. The demographic collapse that followed the volcanic winter and the plague was not a sudden dramatic event like a battle or a siege. It was a slow withdrawal, a thinning of the human presence across landscapes that had been farmed and inhabited for centuries until the forest crept back over fields that no one was left to tend, and the silence of an emptied countryside settled over regions that had once sustained thriving communities. The Scandinavian gold hoards offer a different kind of testimony. More than 1,500 caches of gold objects, rings, bracteates, ornamental pieces have been found, buried across Sweden, Denmark and Norway dated to the 6th century. These were not grave goods or ritual offerings. They were wealth hidden in the ground by people who expected to return and retrieve it. The sheer number of hoards that were never recovered tells its own story. Across a span of just a few decades, enough people died or fled that their buried treasure remained undisturbed in the soil for 14 centuries, waiting to be found by modern archaeologists with metal detectors and trowels. Each hoard represents a small private catastrophe, a family that saw darkness coming and tried to preserve something of value for a future they did not survive to reach. Multiplied by 1,500, the hoards become a demographic portrait of a society in collapse, losing people faster than the survivors could maintain the memory of where the gold was buried. In the eastern Mediterranean, the silence took a different form but carried the same weight. Urban populations that had sustained cities for centuries contracted so dramatically that the physical infrastructure of urban life could no longer be maintained. Aqueducts that had carried water to Constantinople's 500,000 residents fell into disrepair, not because the engineering knowledge was lost, but because the population served by those aqueducts had shrunk to a fraction of its former size, and the tax base that funded maintenance had contracted proportionally. Roads that had connected the empire's provinces deteriorated as the trade they carried diminished. Public buildings were abandoned or repurposed, their stones scavenged for smaller, more modest constructions. The great bathhouses that had been central to Roman social life closed as the populations that used them disappeared. Archaeology reveals this process in stratigraphy layers of occupation, giving way to layers of abandonment, sophisticated structures overlaid by crude repairs, or simply by the gradual accumulation of debris that marks a building no one is using anymore. The economic consequences extended far beyond the immediate regions of population loss. The network of Mediterranean trade that had connected civilizations from Spain to Syria for more than a millennium contracted to a shadow of its former reach. Shipwreck evidence, the number and distribution of vessels lost at sea in different periods, shows a dramatic decline in maritime commerce during the mid to late 6th century. Fewer ships meant less trade. Less trade meant less revenue for the states that taxed it. Less revenue meant less capacity to maintain armies, build infrastructure, or respond to the next crisis when it inevitably arrived. The interconnected economic world of late antiquity was fragmenting into smaller, more isolated units, regional economies, that produced for local consumption rather than for export communities that became more self-sufficient. Not by choice, but by necessity, as the networks they had once depended on ceased to function. In China, the pattern expressed itself through the lens of imperial politics. Tax records from the northern dynasties show precipitous drops in registered households during the 540s, and 550s, a proxy for population decline so severe that entire administrative districts became ungovernable. Imperial granaries that had been maintained as buffers against regional crop failures were emptied and not replenished. The fragmentation of the Northern Wei dynasty, already underway before the volcanic winter, accelerated as provincial authorities lost the ability to collect taxes, feed armies, or maintain the infrastructure that connected the empire's far-flung territories. The Chinese response included both defensive measures, strengthening border fortifications against steppe nomads driven southward by the same climate crisis, and absorptive ones, incorporating some nomadic groups as military settlers along the frontier trading land for loyalty, in an arrangement that acknowledged the empire's diminished capacity to defend its borders through conventional means. What all these regions shared, despite their vast geographic and cultural differences, was the experience of a silence that lasted far longer than the volcanic winter itself. The atmospheric aerosols cleared within a decade or so. The sun returned to its full brightness. Temperatures gradually stabilized. But the human systems that had been disrupted, the agricultural knowledge, the trade networks, the demographic foundations of urban life, the institutional capacity of governments did not recover on the same timeline. Populations that had been halved by famine and plague could not rebuild in a generation. Agricultural land that had reverted to forest could not be cleared and cultivated again without labour that no longer existed. Trade networks that had collapsed could not be restarted without the merchants, the ships, the warehouses, and the trust between distant partners that had taken centuries to develop and had been lost in a decade. The volcanic winter lasted perhaps 15 years. The silence that followed lasted for centuries, and in some places the world that existed before 536 never fully returned at all. What emerged instead was something different, smaller, more fragmented, more cautious, and the shape of that new world is what the remaining chapters must trace. What survived? Not everything fell. That is the part of the story that resists the gravity of catastrophe, the part that complicates any narrative of total collapse. While empires contracted and cities emptied, and trade networks dissolved into fragments, certain communities held together, not because they were spared the volcanic winter or the plague, but because something in the way they were organised allowed them to absorb the shock without shattering entirely. The question of what made the difference has occupied historians for decades, and the answers that have emerged are less dramatic than the collapses they explain, more structural than heroic, more about systems than about exceptional individuals. But they may be more important because they speak to something that matters beyond the 6th century, the qualities that allow human societies to endure when the conditions they were built for cease to exist. The Eastern Roman Empire's survival has already been noted, and the reasons geographic diversity, administrative redundancy, a professional bureaucracy capable of functioning through crisis, are genuine. But the more revealing examples may come from smaller, less prominent communities that left fewer written records but whose persistence is legible in the archaeological evidence. In parts of Ireland, monastic communities that had been centres of learning and agricultural production before the crisis continued to function through the worst years of the 540s and 550s. The monasteries were not wealthy by continental standards, but they possessed something that proved more valuable than wealth: organisational coherence and a culture of record-keeping that preserved knowledge across the disruption. Monks continued copying manuscripts, not just religious texts, but practical documents, agricultural calendars, medical knowledge, historical records. They maintained gardens and small-scale food production, adapted to local conditions. They provided a social structure around which scattered rural populations could organise when secular authority failed. The survival of Irish monasticism through the 6th century crisis is one of the reasons that Ireland became, in the following centuries, a crucial repository of classical learning that had been lost elsewhere in Europe, not because the monks were heroic, but because their institutional structure happened to be resilient in ways that larger, more complex systems were not. A similar pattern appears in parts of the Byzantine East, where village-level communities in Anatolia and the Levant maintained agricultural production through the crisis years at reduced but sustainable levels. Archaeological surveys of rural settlement patterns in these regions show continuity, where urban centres show collapse. The same villages occupied the same field systems in use. The same basic agricultural techniques applied even as the cities those villages had once supplied shrank to fractions of their former populations. The villages survived because they were in a sense less optimized than the cities. They were not dependent on long-distance supply chains or specialized economic roles. They produced most of what they consumed locally. When the trade networks failed, they lost access to luxury goods and specialized products, but they did not lose the ability to feed themselves. Their very simplicity, their lack of the sophisticated interdependencies that made cities powerful and productive in good times became an advantage when those interdependencies became liabilities. The steppe nomads who migrated westward during the crisis also demonstrated a form of resilience, though it looked nothing like the monastic preservation of Ireland or the village continuity of Anatolia. The Avars, the Gukturks, and other nomadic confederations that emerged from the 6th century upheaval were not simply refugees. They were societies reorganizing themselves around new political structures capable of managing the uncertainty that the old climate regime had imposed. The confederations that formed during this period were larger, more politically sophisticated, and more militarily organized than the tribal groupings that had preceded them, adaptations to a world where local resources could no longer be relied upon, and where control of territory across vast distances became necessary for survival. The nomads did not preserve old knowledge or maintain old systems. They built new ones forged in the pressure of ecological catastrophe and refined through the experience of migration conflict and the constant negotiation between mobility and settlement that defined steppe life. Their resilience was not the resilience of continuity, but the resilience of transformation, the willingness to abandon what no longer worked and create something that might. What these diverse examples share is not a single strategy, but a common quality: flexibility. The societies that survived the 536 crisis were those capable of adjusting their fundamental operations when conditions demanded it. The Byzantine bureaucracy could redistribute resources across regions. The Irish monasteries could maintain small-scale self-sufficiency while preserving intellectual capital. The Anatolian villages could contract their economic horizons without losing their agricultural base. The steppe nomads could reorganize their entire political and social structures in response to environmental change. In each case, survival depended not on strength in the conventional sense, not on military power or wealth or technological sophistication, but on the capacity to adapt to let go of what was no longer viable and to reorganize around what remained possible. The civilizations that collapsed Teotihuacan, with its rigid ceremonial hierarchy, the Sassanid Empire with its concentrated agricultural dependence, the countless smaller communities whose names were lost when no one survived to remember them, shared a different quality optimization without margin. They had built systems that were extraordinarily efficient under the conditions that had prevailed for generations, but that contained no mechanism for fundamental reorganization when those conditions changed. Their very success had made them brittle. The volcanic winter did not select for the strongest societies. It selected for the most adaptable, and those are not always the same thing. The lesson is not comfortable because it suggests that the qualities we most admire in civilizations, complexity, specialization, efficiency, interconnection, may also be the qualities that make them most vulnerable to sudden unpredictable disruption. The societies that endured the darkness of 536 were not the most advanced or the most powerful. They were the ones with enough flexibility to bend when the world shifted beneath them, enough redundancy to lose parts of themselves without losing everything, and enough humility, though they would not have used that word to recognize that the old ways had stopped working and that something new was required. It is a pattern that did not end with the 6th century, and it carries implications that reach well beyond the ancient world into questions about resilience and fragility that remain unsettled in our own time. The sun returns. How long does it take for a world to remember that it was once different? The atmospheric aerosols from the final eruption in the cluster settled out of the stratosphere sometime in the early 500s. The sulfate concentrations in the ice cores dropped back toward baseline. The tree rings slowly over the course of the following decade began to widen again, not to their pre-536 dimensions. Not immediately, but enough to indicate that the growing seasons were lengthening. The temperatures were climbing back towards something the trees and the soils and the seeds recognized as normal. The sun, by the accounts that survived from this period, returned to its full brightness. The dry fog cleared. The sky, for the first time in nearly 2 decades, looked the way the sky was supposed to look. But the world beneath that sky bore almost no resemblance to the one that had existed before the dimming began. European population levels would not recover to their pre-536 numbers until the 8th century, 200 years of demographic deficit. 200 years during which there was simply not enough people to maintain the infrastructure, the agricultural output, the trade networks, and the institutional complexity that had characterized the late antique world. In some regions, the recovery took even longer. Parts of Mesopotamia that had been continuously farmed since the Bronze Age would never fully return to their former productivity. The irrigation systems too thoroughly degraded the soil, too deeply salinized the knowledge of how to maintain those systems lost, along with the populations that had possessed it. The Sassanid Empire would hold together for another century in diminished form before collapsing entirely. The Byzantine Empire would survive for nearly a millennium longer, but as a smaller, more defensive, more cautious state than the expansive power Justinian had envisioned. Teotihuacan would stand empty until the Aztecs found it, and wondered as we still wonder what kind of people had built such a place and why they had left. The medieval world that emerged from the 6th century crisis was shaped by the memory of catastrophe, even when that memory was not explicit. The labour shortages created by population collapse altered the relationship between landowners and the people who worked their fields. Peasant labour became more valuable. Serfdom evolved into forms that, while still exploitative, offered marginally more security than the arrangements that had preceded the crisis. The political fragmentation of Western Europe, already underway before 536, accelerated into the patchwork of kingdoms and principalities that would define the medieval period. The monasteries that had survived the darkness became the custodians of knowledge that might otherwise have vanished entirely, not just religious texts, but practical wisdom about agriculture, medicine, construction, and law preserved in manuscripts copied by hand in cold scriptoria by monks who understood perhaps better than anyone how easily the accumulated learning of centuries could disappear. The Justinianic plague continued its recurring waves until the mid-8th century, each outbreak smaller than the last, the bacterium gradually losing its foothold in Mediterranean rodent populations until it retreated into the wild reservoirs from which it had emerged. Genetic analysis has confirmed that this particular lineage of Yersinia pestis eventually went extinct. It is not the ancestor of the Black Death strain that would devastate Europe 800 years later. The two pandemics were separate branches on the same evolutionary tree-independent emergences, driven by different circumstances but exploiting the same human vulnerabilities. Density malnutrition disrupted ecosystems, the movement of goods and animals along trade routes that served equally well as highways for a disease. The parallel is instructive without being predictive. History does not repeat in precise patterns, but the conditions that enable catastrophe, ecological disruption, agricultural dependence on narrow climate windows, the fragility of complex interconnected systems are not unique to any particular century. The volcanic systems that produced the 536 crisis have not become less dangerous. Ilopango, if it was indeed the source of the initial eruption, remains an active volcanic complex. Iceland's volcanic systems continue to produce eruptions capable of stratospheric injection. Indonesia, the Philippines, and the Cascades of the Pacific Northwest all contain volcanic systems that have produced eruptions of comparable or greater magnitude within the geological recent past. The question is not whether another such event will occur, but when and whether the civilizations that experience it will possess the adaptability that distinguished survivors from casualties 1500 years ago. Our monitoring systems are vastly superior. Our scientific understanding of atmospheric chemistry and volcanic climate forcing is detailed and precise. But our global population is 40 times larger than it was in the 6th century. Our agricultural systems are more productive, but also more specialized. and our supply chains are longer, more complex, and more vulnerable to disruption than anything the Roman or Sassanid empires maintained. The ice still holds its record. The trees still carry their rings. The abandoned cities still stand in their silence, offering testimony to anyone willing to read it carefully and without the comfort of certainty. The sun came back after 536. It always does. But what it illuminated when it returned was a world that had been remade by its absence, quieter, smaller, more fragile in some ways, more resilient in others, and haunted by an experience that the people who lived through it could describe but never fully explain. We are only now 15 centuries later beginning to read the evidence they left behind, and perhaps the most honest thing that can be said after following the traces this far is that the reading is not finished. The ice has more to tell, the trees have more to remember, and somewhere beneath the surface of the present the Earth is doing what it has always done, building pressure, accumulating heat, waiting with a patience that makes human memory seem very brief and very young. That thin layer of sulfate in the Greenland ice core, the one drilled from 2 miles of compressed snow in 1992, dated to a year when the sun dimmed and half the world stopped keeping accurate records of its dead, is still there. It has not changed. The chemistry is the same as it was when the snow first fell 15 centuries ago, capturing whatever drifted through the atmosphere in that terrible season and holding it with a patience that makes human archives seem fragile and brief. If you could hold the core in your hands, you would not see anything remarkable. A faint discoloration, perhaps. A slight difference in the clarity of the ice. Nothing that announces itself as the record of a catastrophe that reshaped civilizations across 3 continents. The evidence is there, but it is quiet, the way most evidence is quiet, waiting not to be noticed, but to be read by someone willing to look closely enough and slowly enough to understand what they are seeing. We have followed that evidence across a long distance tonight, from the ice sheets of Greenland to the tree rings of California and Scandinavia, from the careful prose of a Byzantine lawyer watching the sun fail over Constantinople to the spare notation of an Irish monk recording a failure of bread, from the sulfate chemistry of ancient snow to the scorch marks on temple walls in a city that burned itself rather than endure a silence its gods could not explain. From the DNA of a bacterium extracted from the bones of people who died in mass graves they never expected to fill. Each piece of evidence illuminated a small portion of the picture, and together they formed something that resembles understanding, but only resembles it because the picture is not complete and perhaps it never will be. There are volcanoes that have not been conclusively identified. There are mortality figures that remain estimates built on estimates. There are causal chains that seem logical but cannot be verified with the tools currently available. There are civilizations whose collapse may have been triggered by the volcanic winter, or merely accelerated by it, or shaped by forces we have not yet learned to detect in the archaeological record. The uncertainty is not a failure of the science. It is the nature of the inquiry, the honest condition of trying to reconstruct events that happened 1500 years ago from fragments of ice and wood and bone and ink, none of which were created with the intention of being read by anyone, let alone by us, let alone now. And perhaps that is enough. Perhaps it is enough to know that the evidence exists without demanding that it resolve into a single clean narrative. The ice holds its sulfate. The trees hold their narrow rings. The abandoned gold hoards of Scandinavia hold the memory of families who buried what they valued most and never came back for it. These are not answers. They are traces marks left in the physical world by events that exceeded the capacity of any single witness to comprehend. We do not need to decide tonight what they mean in total. We only need to acknowledge that they are there, that they speak to something real, and that the conversation between the evidence and our understanding of it is still unfolding, still incomplete, still open to revision in ways that make the inquiry worth continuing rather than worth closing. One question remains, and it is not the kind that demands an answer before sleep. If the sun dimmed again tomorrow, if the sky turned pale, and the summers went cold and the harvest failed, for reasons no one could see, what would we preserve? What would we bury in the ground, hoping to return for it? What would we copy by hand in quiet rooms, believing it mattered enough to survive? The people of 536 made their choices. Some of those choices endured, most did not. But the impulse, The refusal to let everything disappear without leaving some mark, some record, some small act of preservation against the dark, that impulse is still here. It is in its own way the most durable thing they left behind. Let that thought settle now if it wants to. Or let it drift. The ice is patient. The trees are patient. The story will be here in the morning if you want to return to it. For now the room is quiet, the air is still, and there is nothing required of you, no evidence to weigh, no mystery to solve, no pattern to trace through the sediment of centuries. Just rest, traveller. The sun came back. It always does. And the silence that follows a long story is not emptiness. It is the space where sleep begins.